In this video, we evaluate this antiderivative using a method called trigonometric substitution. Now, one thing I want you to notice with this is we've got a quotient. So certainly we don't have a basic rule for that. There are no basic anti-differentiation rules for quotients. There's no quotient rule for antiderivatives. And also we've got a function nested inside another function. I've got this 1 minus x squared under the radical, and that might indicate to me that I want to try a U substitution. But if I take the derivative of this inside function, derivative of 1 is 0, the derivative of negative x squared is negative 1 times that 2 because we bring the power down times x to the 1 less power. Actually, let me write that out. So du is the derivative of this, which is 0 minus, bring the power down, multiply by x to the 1 less power times dx. And we don't have this negative 2x dx there up in the integrand. Now, we can always adjust the constant, so we're never really worried about the 2. We can always multiply or divide by just the right thing to make the constant what we want it to be. But when I'm trying to decide whether or not U substitution will work, I compute this du, and then I look at it and I say, is there an x dx up there somewhere? And there's not. I've got an x to the 4th, but it's in the denominator. That's really a 1 over x to the 4th. So U substitution is not appropriate here, and we should try something else. One of the things that we notice is that this integrand does have a 1 minus x squared in it, and that kind of looks like this antiderivative. It's one of our basic rules that we learned in Calculus 1. Oops, there should be an a squared there. It's the integral of 1 over the square root of a squared minus x squared with respect to x. In Calculus 1, we showed that the derivative of arc sine of x over a with respect to x could simplify to become this. So the antiderivative of this is actually equal to this plus c. And I want you to notice the similarity between this a squared minus x squared here and the 1 minus x squared here. The a is just a constant. And so if I see a constant minus my variable squared, I'm thinking that might be an arc sine if it looks exactly like this, or maybe there's a different constant in the numerator that we can factor out. But if I don't have something that looks exactly like this, and it's not an arc sine, and it's not a U substitution, then in the trigonometric integral section, we said if it looks like an arc sine, but it's not an arc sine, and it's not a U substitution, then we're going to make a sine substitution. So it looks like an arc sine, but it's not one, we make a sine substitution. So we'll say since the integrand involves that a squared minus x squared, we're going to make the substitution x equals a times sine of theta. So that's the plan. And if it looked slightly different, if it looked more like the arctangent antiderivative, we would make a tangent substitution. If it looked like the arcsecant antiderivative, we'd make a secant substitution. But because we've got that constant minus our variable squared here, and there's a constant minus the variable squared in this rule, that reminds us that we make the sine substitution. Now you actually don't have to memorize that. It's on your guidelines for trigonometric substitution, so you can always use that as well. Okay, so if we didn't have our guidelines, we would know that we should let x equal a times sine of theta because of this pattern. It's not an arc sine, it's not a U sub, but it looks like an arc sine because it has that a squared minus x squared in it, so we're going to make a sine substitution. Now, in order to do that, we need to prepare to substitute. The first thing that we do when we prepare to substitute is we identify a, first by identifying a squared. A squared is that number that you're subtracting the x squared from. And then you take the positive square root of that to get a. In this case, a is equal to 1. Then we let x equal a, which happens to be 1, times sine of theta. Again, because of the form of that integrand. And we're preparing to substitute. So we want to write everything up here in terms of theta rather than x. If x is equal to sine of theta dx, in terms of theta is the derivative of sine of theta, which is cosine of theta, times d theta. And this square root expression, the square root of 1 minus x squared, it can be written in terms of theta as well. Now we could just substitute sine of theta in right there, but I prefer to simplify the whole radical expression before I substitute. It just makes the substitution a little cleaner. So we've got the square root of 1 minus x squared, and x was sine of theta, so I'm going to substitute that in. And sine of theta, quantity squared, is sine squared theta. Now there is a Pythagorean identity from trigonometry. And it says the following: if you take sine squared of an angle and you add cosine squared of the same angle, you get 1. Now, if I rearrange this by subtracting sine squared from both sides, we see that cosine squared of an angle is 1 minus sine squared of the same angle. And that is what I have under here, except my angle is theta rather than just this a that I have on the right. So this becomes the square root of 1 minus sine squared, which is the square root of cosine squared theta. And with an appropriate range of values for theta, this will just be cosine of theta. In our class, for these substitutions, whoops, sorry, having a little trouble with my camera today. For these substitutions, the range of values is always such that we can take the square root of cosine squared and just get cosine of theta. It really has to do with the arc sine domain and range, and the range of values, or excuse me, yeah, the range of values that we get for the cosine function. But all of that is discussed in the videos that we have over trigonometric substitution if you're interested. Okay, so we've prepared to substitute by evaluating all of these expressions. That's our first big step, is to prepare to substitute, choosing the correct substitution, computing our dx, and then evaluating that a squared minus x squared expression. And since it had a radical around it, we evaluated it with the radical around it as well. Now we're going to substitute. So we've got the integral of the square root of 1 minus x squared over x to the 4th with respect to x. And then we're just going to make replacements. Everywhere we see a function of x over here, we need to replace it. Sorry about that. My video is going a little bit haywire today. It's not a problem though. We can make the best of any situation. So we've got the square root of 1 minus x squared, which is cosine of theta. I'm literally replacing this with cosine of theta. And that dx on the right, I am literally replacing that with cosine of theta d theta. Oops. Sorry about that again. Alrighty, and then that denominator, it has an x to the 4th in it. We don't have an x to the 4th here, but we do have an x. So that 4th power is still there, and we're going to replace the x with sine of theta. All right, so that is our new integrand written in terms of theta. The whole point of a trigonometric substitution is to be able to write that integrand in terms of theta, and then because we are familiar with techniques for evaluating trigonometric integrals from our studies at the last section, we will be able to evaluate this integral. We might have to use some trig identities. We may have to use our guidelines for powers of sine and cosine or powers of secant and tangent, but we can evaluate this integral. So let's simplify from here. If you want to, you can write this cosine of theta as itself over 1. You've got two fractions. You're just going to multiply straight across. Cosine times cosine is cosine squared theta. And then the sine to the 4th of, or sine of theta to the 4th can be written as sine to the 4th of theta. And then we've got the d theta there. Now, many students, because we just used this identity, cosine squared equals 1 minus sine squared, often want to apply that here. And you can if you want to, but I highly recommend using this other technique instead. And the reason I'm using it is just because it works. Often we do a lot of trial and error when trying to rewrite an integrand in order to get it into a form that we can anti-differentiate. If we substitute that here, we might make some progress, but we're probably not going to get where we want to go as efficiently as if we do what I'm about to do. So here's what I chose to do. This cosine squared over sine squared, two of these sines, would give me a cotangent function. Because remember, from trigonometry, we learned the following fact. If you have cosine of an angle divided by sine of that angle, that turns out to be tangent of that angle. And 1 over sine of an angle is cosecant of that angle. So this cosine squared over sine to the fourth can be rewritten in the following way. I can leave a cosine squared over sine squared as one factor, and then I can factor out a 1 over sine squared over here. If you're saying, how did you know to do that? Well, I'm just thinking about how I can rearrange this, knowing what I know about our trig functions. Since I know that cosine, is, or cosine over sine is cotangent. I don't know why I wrote tangent. Cotangent of that same angle. I want to reorganize this so that this looks like a cotangent. Now, if that's squared, I need the denominator to be squared. So I take a cosine squared and I sort of group it with this sine squared, knowing that cosine over sine can be written as cotangent. And then 1 over sine squared is related to this 1 over sine. Since 1 over sine of an angle is cosecant of that angle, 1 over sine squared of that angle is cosecant squared of that angle. And cosine squared over sine squared is cotangent squared. Now, we do not have a basic rule for this. We've got basic rules for lots of antiderivatives, including cosecant times cotangent, but not cosecant squared times cotangent squared. That might concern you. Don't be concerned. If you can still identify a function here whose derivative is part of the integrand, then we can still evaluate this integral. And we have a couple of facts. If we look at the cotangent derivative with respect to theta, it turns out to be negative cosecant squared of that angle. So that means I've got this cosecant squared of theta d theta. That is almost exactly the derivative of cotangent of theta. So that means I can evaluate this antiderivative using a U substitution. Cotangent of theta can be written as cotangent of theta, or cotangent of theta squared, can be written as cotangent of theta quantity squared. So that can be thought of as a U squared, and the derivative of U is almost cosecant squared theta d theta. It's not quite there. We need this extra negative sign, and we will take care of that because we can always adjust the constants as I mentioned before. So let's actually do that. Oops, that's for another problem. Sorry about my video, it's being a little buggy today. That's okay though. We can handle anything. No matter what happens, we can always handle it. All righty. So we're here. And we want to write this integral entirely in terms of u, where u is equal to the cotangent function. And again, that's because the derivative of cotangent is up here as a factor. The derivative of cotangent of theta is negative cosecant squared theta d theta. And while I don't have the negative sign, I do have the cosecant squared theta d theta. And that tells me a U substitution will work. Now, since I don't have the negative, I want to get rid of the negative on this line. So I'm going to solve this equation for cosecant squared theta d theta. I can do that if I multiply both sides by -1. Okay, so then our integral becomes the integral of, well, I'm going to rewrite it in a slightly different order. this cotangent of theta squared. I think I want to write that first. And then I'm multiplying by cosecant squared theta d theta. And I'm just organizing it in that way so that this du piece is over on the right and the function of u is over on the left. But either way is fine because we can multiply in whatever order we want, right? This times this is the same as this times this. That's called commutativity. Anyway, this can be thought of as u raised to the second power, and cosecant squared theta d theta, well, according to this, that is -1 times du. So the integral can be written in terms of u in the following way. This is u, just replacing the cotangent of theta with a u, and then that second power is still there. So I write the second power down. And then this piece is replaced by a -1 times du, and that negative can be pulled out front. And so now we have the integral of u squared with respect to u times -1. Now, the whole point of a u substitution is to get this integral that we have in terms of u. And our hope is that this integral will be something that we can evaluate using one of our rules. We ask ourselves, after the u substitution, do we have a rule for that? If we have a rule for that, we just go ahead and apply it. And we do have a rule for that. The rules look like this. We've got the integral of x to the n with respect to x. That's x to the n plus 1 over n plus 1 plus c. Or sometimes I'll write it with the n plus 1 factored out. So we've got a 1 over n plus 1 times x to the n plus 1 plus c. Of course, this is provided that n is not equal to -1. And in our case, we've got an n equals 2. Now, if you're saying to yourself, that does not look exactly like that, you're right. We have a different variable, but the variable that we're anti-differentiating with respect to really doesn't matter. It's just a dummy variable. It's a placeholder. This says, whatever you have here, anti-differentiate it with respect to u. So we'll do that. First, we bring the constant down. And then according to this rule, we add 1 to the exponent. 2 plus 1 is 3. Then we keep that base exactly the same. And then we divide by the new exponent. And then we add c. Now, I prefer to write that as a -1 over 3 times u cubed. Now, we're not finished with our u substitution yet. The whole point of a u substitution is to find this antiderivative, and that is a function that we can take a derivative of and actually get this cotangent squared theta times cosecant squared theta back. If I take the derivative of this with respect to u, I'm not going to get a function of theta back. So I need to write my answer in terms of theta. The u sub just allowed us to take the antiderivative by writing this in a form that we had a rule for. So we wrote it in the form that we had a rule for, then we applied the rule, and now we'll back substitute. So we've got -1/3 times u cubed plus c. And u, in this case, was cotangent of theta. That was a substitution that we made way up here. Okay. So we've got u, we compute du. Then we write the integral in terms of u. And then this is a very important step. After you simplify, don't forget to anti-differentiate. The whole point is to be able to anti-differentiate that using a basic rule. And we were able to, it's just a power rule. And then the last thing that we do with a u substitution is we always back substitute. That means we're going to go in and replace u with whatever it was, in this case, in terms of theta. That was cotangent of theta. All right. So I know it's a lot of steps, but I want you to think about the big picture here. As far as our trigonometric substitution is concerned, we started by preparing to substitute. And then after we prepared to substitute by identifying x, or defining x, excuse me, computing dx, and then simplifying the square root of 1 or 1 minus x squared, or in general, a squared minus x squared. After doing all of that, then we write the integral in terms of theta so that we can evaluate it. So what we called this step in class was substituting, simplifying, and anti-differentiating. Now I know that there's a lot to that, but the idea is this: when we make a substitution, we're preparing to substitute, then we substitute, and the whole point of the substitution is to be able to anti-differentiate. And we did. We simplified, we used trig identities so that we would write this in this way. Then we were able to use a U sub to evaluate that antiderivative. So we did the U sub, which involved writing the integral in terms of U, computing an antiderivative, and back substituting. But that is that sort of second step with in the big picture with a trigonometric substitution. We are trying to write everything in terms of theta so that we can take the antiderivative, and we did. But of course, just like with a U substitution, our goal is not to get a function of theta. Our goal is to get a function of x, because we want to be able to take the derivative of that function of x and actually get that integrand back. Because remember, we're computing an antiderivative. If we take the derivative of the result, we should get this right here, because antiderivatives and derivatives undo each other. They're inverse operations. Okay, so I've got this function of theta, and what I really want is a function of x. In order to find that function of x, we go through our next step. Here we're going to draw a triangle and label the sides. In terms of x. And then we're going to use that triangle to find cotangent of theta in terms of x, and we'll substitute it into our answer. Okay, now whenever we are drawing and labeling the sides of this right triangle, and it's always a right triangle, we always use our original substitution. So in this case, we had x equals sine of theta. So I'll draw a right triangle. There's my theta. And I'm thinking of sine of theta as a fraction. We always think of these trig functions as ratios. This is x over 1. And remember from trigonometry, we had this mnemonic device, SOHCAHTOA, that reminded us that sine is actually opposite over hypotenuse. It's the ratio of the length of the side opposite theta and the length of the side opposite the 90-degree angle, which we call the hypotenuse. So this sine of theta equals x over 1 can be thought of as giving us an opposite and a corresponding hypotenuse relative to theta. So this is saying, okay, if this is my angle theta, when the side opposite theta, that's directly across from theta, is equal to x, at that time, the hypotenuse would be equal to 1. Then you can use the Pythagorean theorem to find the length of the third side, or you can just look at your sheet. This squared, or this squared plus this squared has to give us this squared. So to find this side, it's this squared, or this length squared minus this one, and then you take the square root. You could write all that out. I'm not going to in this video, but if you use the Pythagorean theorem, you can find this side, or you can just look at the sheet, and the sheet will show you the square root of a squared minus x squared on the adjacent side of this triangle for the sine substitution. Okay, so I've got this triangle, and this is great because it labels, all three sides, which we can think of as opposite of theta, adjacent to theta, and the hypotenuse of this triangle. It labels all of those in terms of x. And that means I can find sine in terms of x, I can find cosine in terms of x, I can find tangent in terms of x. And because of our reciprocal identities, we can find cosecant, secant, and cotangent in terms of x. We can find them all because we've got all three sides of this triangle. Now, our goal for this particular problem is to write this negative 1/3 cotangent of theta quantity cubed plus c in terms of x. So what we need is to find cotangent of theta using this triangle. And it's actually relatively easy to do. Cotangent of theta is 1 over tangent of theta. So if you did not remember what cotangent was in terms of adjacent, opposite, and hypotenuse, those sides of the triangle, you could just go over here to your tangent mnemonic from SOHCAHTOA. This says that tangent is opposite over adjacent. And then remember your reciprocal identity. Cotangent is 1 over that. So if tangent is opposite over adjacent and cotangent is 1 over that, we just flip those. Instead of getting opposite over adjacent, we're going to get adjacent over opposite. The adjacent side, that's the side next to theta that's not the hypotenuse, it's adjacent to theta, is the square root of 1 minus x squared. And the opposite side is across from theta in our triangle, and it's just given by x. So the square root of 1 minus x squared over x is what we're going to substitute right here. We are literally going to replace this with this. And then we're going to do a little algebra to simplify, and that's going to be our final answer. Okay. Different class. All righty. So my answer was negative 1/3 cotangent of theta cubed plus c. And from the identity on the last page, we found that cotangent was the square root of 1 minus x squared over x. So we are going to substitute that in for cotangent right here. Now, a couple of things. Probably wouldn't leave my answer like this. Probably want to simplify it, especially if I was checking my answer against the answer in the back of the book. It's not probably not going to look at this. A couple of ways that we could simplify it in the following ways. If we had the nth root of x and we were raising it to the m, we can think of that as this. This is x raised to the m divided by n. So the index of the radical goes in the denominator, and that power that's outside or inside the radical, either one would have been fine, that goes in the numerator. So this piece goes right here. So that means when I have the square root of x minus, or 1 minus x squared, and remember with the square root of x, there's always an implied 2 there. That means this piece is actually the square root of 1 minus x squared, and then we're going to take that and cube it. If you're saying, how can I just cube that? That's because of this other fact from algebra. If we've got a quotient and we're raising it to a power, we can raise the numerator to that power and the denominator to that power. So this is negative 1/3 times this expression cubed over the x cubed, applying that third power to the numerator and the denominator. And then this can be thought of this way. That 1 minus x squared under the radical stays exactly the same. And this says cube it and then divide by 2. So raise it to the 3/2 power. The index of the radical goes in the denominator, and if it looks like there's no index there, it's an implied 2, because that's a square root. The square root, we just don't write the 2. We still have the x cubed in the denominator. And now I've got 2 fractions, and I can multiply straight across to write a single fraction. This is giving us 1 minus x squared raised to the 3/2 over 3x cubed. And we still have that negative 1 out front. And that is our final answer. And that's how we use trigonometric substitution in general. So you prepare to substitute, identify A, define X to be A sine theta. If you have that A squared minus X squared in your integrand, compute DX, simplify that square root of A squared minus X squared, then substitute. Replace the square root with this. Replace the dx with cosine theta d theta. Replace the x in the denominator with sine of theta. But don't forget to raise it to the 4th power. Then you substitute, simplify, and anti-differentiate. That may require your trigonometric integrals techniques. That may require, sorry about that, little buggy issue with my cameras again. May require U substitution. In this case, it required a U substitution. So we did the U substitution, and then of course, don't forget to back substitute. And you're going to have an answer in terms of theta. That's not what you want. You want an answer in terms of x, because our goal is to find a function that we could differentiate that would give us this back as its derivative. In order to find that answer in terms of x, we draw a right triangle and we label the sides of that triangle in terms of x using our original substitution. So we say sine of theta is this. From right triangle trig, sine is opposite over hypotenuse. We label the side opposite theta. We label the hypotenuse of the triangle. We use the Pythagorean theorem to get the third side, or you can just use your reference sheet, either way. And then you look at this triangle and you use the triangle to find that answer in terms of x. And I'm really not even looking at the -1/3 or the plus c or that cubing, that third exponent there, excuse me. Cubing function is what I was thinking. I'm looking at the trig functions and I'm saying, okay, I've got a cotangent in my answer. I need cotangent in terms of x. So I write my cotangent in terms of opposite, adjacent, and hypotenuse. And if I don't remember this, hopefully I remember the reciprocal identity and this identity, or this mnemonic. Tangent is opposite over adjacent. So cotangent is adjacent over opposite. Take the adjacent side, take the opposite side, substitute them in. Now you've got cotangent in terms of x. Great. That means you know what this is in terms of x, so you can write your answer in terms of x, which is what we did right here. Replace that cotangent with this function of x, and then you just do a little bit of algebra to simplify. And usually we like to write it, if it's a product like this, we usually like to write it as 1 simplified fraction plus c. And that's our final answer. And I guess we should write that our 4th and final step was to write the answer in terms of x using, I'm going to say the triangle, but again, it's really that the triangle allows us to find cotangent in terms of x, and then we substitute. I hope that helps. Honestly, whenever you're taking a math class, it's really important that you're not just proficient at watching other people work problems, but you can work the problems yourself. I hope that every step in this method made sense to you. If there's any part of the method that doesn't make sense to you, let me know. But our goal is not for you to just be able to follow along and watch me work this problem, but for you to follow a similar procedure to solve any problem that's similar to this. So the goal is really for you to be able to do this independently. Remember that, and it's not, when I say that, it's not because I don't want to help. I always want to help you. But helping you means helping you to become independent. I could work these problems all day, but that doesn't necessarily mean that you'll be able to work them all day. The important part is that you can see what I'm doing, see what I'm modeling for you, and then try to really do that yourself. If there's any step in this process that you don't understand, let me know. If you have to go through it slowly and you're not really sure of why you're doing what you're doing, just go ahead and take your time and slow down and make sure that you completely understand that step. And if you don't, that's when you should absolutely ask for help. But remember, the goal is for you to do this, not for me to do this. And while I'm happy to work lots of problems for you, it's important that we get to the point where you can do it on your own, and you're not just watching me solve problems. Because it's really easy to fool ourselves while watching other people solve problems and saying, oh, I get it, I follow along, that was really easy. And then to try it ourselves and to struggle. So your goal is to learn from what I'm doing and hopefully be able to do the same thing independently. Everything I can do, I want you to be able to do after taking my class. So let me know if you have any questions about this particular method, any particular steps. If you have to watch this video over and over again, go ahead and do that. Go ahead and pause it, slow it down. And if there's a point where you have a question and you can't ask it, or you obviously can't ask a video a question, that's when you send me a remind text, send me the timestamp on the video, and I will look at the part of the video that you're asking about, and then we can talk about that part of the method. I really hope this helps you. Talk to you later, Mitch. Bye for now.